This will be the third lecture out of chapter 18. So in this lecture, we'll look at more reactions of aldehydes and ketones. Okay, so we looked at how aldehydes and ketones react with water, with HCN to make cyanohydrins, and with alcohols to make acetals and hemiacetals. And so now we'll look at how, so we'll just change the nucleophile. So now instead of water or CN or alcohol, what if the nucleophile is an amine? So similar mechanisms. So the first few steps in the mechanisms are identical. So in this case, we have an amine. So if the nitrogen has at least 2 hydrogens, so it could be NH3 or it could be NH2R. So whatever the R group is, doesn't matter, it's just tagging along. So long as the amine has 2 hydrogens, and this is the mechanism that it's going to follow. So we're going to, same mechanism as before, we're going to protonate the oxygen, and then the nucleophile is going to attack the carbon and break the carbon-oxygen double bond. And then we're going to lose a hydrogen from the nitrogen, or if it was water, we would lose the oxygen from the H2O, or if it's an alcohol, we would lose it from the OR group. So now we're losing the hydrogen from nitrogen. So this would be the amine version of a hemiacetal. But this doesn't stop there. So we're not going to worry about, you don't have to know this functional group, because as soon as you make this is going to keep on reacting. So we're going to protonate the oxygen again. And now you have a water molecule, so water molecule can leave and take those 2 electrons with it. And to make this carbocation, so this carbocation, so we can take, so this is where the mechanism becomes different, because with the acetals, another alcohol attacked here, but that's not what happens with amines. So what happens with amines instead is we can take this lone pair and make a carbon-nitrogen double bond, and then lose a hydrogen from that nitrogen and make a lone pair on nitrogen and make this as your product, or more commonly be wrote flipped upside down. And so this is a new functional group in organic chemistry for you to know. So if you have a carbon-nitrogen double bond, that's what's called an imine, or sometimes called a Schiff base. So it has a carbon double bond into nitrogen. So how to think about predicting the product. So again, if you just learn to recognize the recipe, if you have an aldehyde or a ketone with a amine, then you're going to lose 2 hydrogens from nitrogen, and then make a double bond from carbon to nitrogen instead, and you have the imine. Okay, so other imine derivatives are very common in organic chemistry. So we can just change out what is there. Instead of an alkyl group, instead of an R group, maybe it's an OH. So this molecule is called hydroxylamine. Same basic concept. You're going to lose water, and nitrogen's going to be double bonded there instead, and whatever's attached to nitrogen is just along for the ride. So basically what we're going to do is we're going to lose the 2 hydrogens from nitrogen. We're going to lose that oxygen, and we're going to have a double bond to nitrogen instead. Right? Doesn't have to look pretty, you just have to have the right molecule. So double bond to nitrogen, and OH is just along for the ride. So that's what's called an oxime. Having a C double bond N with an OH attached is an oxime. Or if you reacted it with this molecule, so that's just along for the ride now. So this is what's called a hydrazine. You have a nitrogen-nitrogen bond. And same concept, we're going to lose water, and nitrogen is going to be double bonded there instead. All right, so we're going to lose 2 hydrogens, we're going to lose oxygen, and we're going to be double bonded to that nitrogen instead. And the NH benzene ring is just along for the ride. So this is what's called a hydrozone, having a C double bond N with another N attached to it. Or you can start with what's called a semicarbazide. So that's where basically now this is just tagging along. So same concept, but we're going to lose water, right? So we're going to lose and double bond nitrogen to that carbon instead. So we're going to lose 2 hydrogens, we're going to lose oxygen, and we're going to have a double bond here instead, and this is just tagging along. And that's what's called a semicarbazone. Okay, so the significance of these, the oximes, hydrozones, and semicarbazones. Well, one significance is that aldehydes and ketones are usually liquids, whereas these derivatives, so these are what are called derivatives of aldehydes and ketones. The oxime, the hydrozone, and semicarbazone are called derivatives of aldehydes and ketones, and they are typically solids. And so solids are easier to work with than gases and liquids. Solids you can just take a melting point on. So there are hundreds and thousands of derivatives of different aldehydes and ketones known, and melting points are taken, and these melting points, the physical properties of the solid derivatives, are published. And then you can just, if you have an unknown aldehyde or a ketone, you can look in the derivatives list and see if you find with a matching melting point, for example, and that will help you figure out what the aldehyde or ketone was. It's less important these days because now we have powerful NMRs, where you can do NMR and IR and mass spectrometry and figure out the structures of your molecules that way. But of course, instrumentation is extremely expensive as well. Okay, so anyway, you should know how to just predict these products. So you just learn the recipe. If you have an aldehyde or a ketone with an amine that's got 2 hydrogens attached, lose a water molecule, double bond nitrogen to the carbon of the double bond, and whatever's attached to nitrogen is just tagging along for the ride. Okay, so now we can understand the mechanism for the Wolfkrishna reduction. So if you remember the Wolfkrishna reduction, if you have an aldehyde or a ketone with hydrazine and base, then you can reduce the C double bond O all the way down to a CH2. So how does that work? Well, what happens if you take an aldehyde or a ketone with hydrazine? You make a hydrozone, as we just saw. And then once you have a hydrozone in the presence of base, then what can happen is, so hydroxide can deprotonate the nitrogen. These electrons become a lone pair on nitrogen. And then we can take this and draw a resonance structure. So take a lone pair, make an N double bond, and those 2 electrons become a lone pair. And then this, so a lone pair on carbon's a very strong base, so this can deprotonate a water molecule. So now you remade your hydroxide, and basically kind of repeat the process now. So now another hydroxide takes the second hydrogen from there. Those electrons become a lone pair on nitrogen. And then we're going to take a lone pair on nitrogen, now make a nitrogen-nitrogen triple bond, and break this other bond. And then that lone pair on carbon picks up a bond from hydrogen from water, and we made hydroxide again. But now you reduce the C double bond O all the way down to a CH2. So what is the driving force for this? The driving force is that N2 molecule that you just made. All right, so N2 is a gas, so entropically that's favorable because you're making a gas in the reaction. And enthopically it's very favorable as well because N2 triple bond is extremely stable. N2 is an extremely stable molecule, right? We're all sitting here breathing about 78% nitrogen gas right now. So it's a very stable molecule. It's very favorable to form, and that's what helps. Losing N2 is what helps drive this reaction. Okay, so what if the amine is secondary? So that means the nitrogen has 2 carbons attached to it. So now it only has 1 hydrogen. So if the amine only has 1 hydrogen on it, then the reaction gives a different product. It's not going to be an amine anymore. You're going to make a molecule that looks like this, and that's a new functional group. That's what's called an anamine. Why is it called an anamine? Well, the En is the alkene, and the alkene has an amine attached to it, right? Okay, so let's go through the mechanism how that works. So the first few steps in the mechanism is identical. So the aldehyde or a ketone, take a lone pair on oxygen, protonate the oxygen. And then the second step is the same, nucleophile attacks. It's just a different nucleophile now. Instead of water or CN or alcohol or primary amine, now it's a secondary amine that attacks there. And break the double bond. And then the third step is the same. Now we're going to lose a hydrogen from the nitrogen. And so if this was water, you would have a hydrate at this point. If this was HCN, you would have a cyanohydrin at this point. If this was an alcohol, you would have a hemiacetal at this point. But with amines, again, they are different. They keep reacting. They don't stop at this point. So we're going to protonate the oxygen, have a water molecule that now leaves. And now, so now this is where it differs from the imine. So if this was a primary amine and you had another hydrogen attached, then you would take the two lone pair electrons on nitrogen and you would make the nitrogen carbon double bond to be an imine. But that doesn't happen with the secondary amine because you don't have a hydrogen on nitrogen anymore. So you don't have a hydrogen that you can lose to neutralize the charge on nitrogen. So what happens instead is you lose a hydrogen from one of the carbons next to the carbocation. So those two electrons become a carbon-carbon double bond, and H plus comes off of the molecule. And now you have an anamine. Okay, so how do you predict the product of an anamine? So first of all, you have to learn the recipe. Aldehyde or ketone plus secondary amine. So if the nitrogen only has one hydrogen attached to it, then basically what you're going to lose is that hydrogen, that oxygen, and that hydrogen is going to become a water molecule. And nitrogen will be attached to the carbon where the C double bond O was at, but then you'll have a double bond adjacent to where the C double bond O was at. You'll have a C double bond C instead. So of course you could have made the C double bond C on either side of the C double bond O. In this molecule it doesn't matter because it's symmetric. Alright, so put the nitrogen with the two R groups that are attached to nitrogen on the carbon that's got the C double bond O, and then make a carbon-carbon double bond off of one of the two sides of the C double bond O, and that would be your anamine. Okay, so I'll try to illustrate that here. So this nitrogen only has one hydrogen, so that's your recipe. It's going to be an anamine. That's the major product. So nitrogen will be attached where the oxygen was. Whatever is attached to nitrogen is just tagging along. But now you're going to have a double bond, C double bond C off to the side. It doesn't matter which side you put it on. But here you have two hydrogens on nitrogen. So that's going to form an imine. So again, we're going to take nitrogen and attach it where oxygen was. But now it's imine, so now we're going to have a double bond between nitrogen and that carbon. Okay, so this will be just slightly harder versions of that same concept. So you have a ketone, you have an amine, and it's only got one hydrogen, so that's your recipe for making an anamine. So now you have to recognize that nitrogen is going to be attached to that carbon. So you're going to make a ring. So if we're going to make a ring, let's number the atoms that will be in the ring. Doesn't matter what you call carbon number one. We just want to have a numbering scheme so that we can get everything in the right spot. Okay, so we're going to make a 6-membered ring. Nitrogen is going to be part of that ring. So we said nitrogen was 6. So if this is 1, 2, 3, 4, and 5, now we can get everything in the right spot. So carbon 1 has a benzene ring attached. 2, 3, and 4 are CH2s. 5 has a methyl. Nitrogen 6 has a methyl. And it's going to be an enamine, so where's the double bond going to be? So if it's a double bond, it's going to have to be either there or there. So if we call this A and we call this B, well, it can't be at A, because if you put a double bond at A, the carbon of benzene has 5 bonds on it. So it's got to be at B. So it's got to be between carbons 1 and 2. So it's got to be there. And now you have an enamine, right? You have a nitrogen attached to an alkene. Okay, here we have an aldehyde. Here we have an amine with 2 hydrogens on it, so that's your recipe to make an amine. So you have to recognize this nitrogen will need to be attached to that carbon, so that's your ring. So 1, 2, 3, 4, 5, 6 membered ring again. So nitrogen will be one of the atoms in that ring. So 6, 1, 2, 3, 4, and 5. Okay, so it's an imine, so the double bond will be between nitrogen and 1, the C double bond, where the C double bond O is at. So 2 is a CH2, 3 has 2 methyls, 4 is a CH2, 5 has a methyl, and nitrogen just has its lone pair. So that would be your imine. Okay, for this one you have a ketone, and you have an alcohol. So that's your recipe for making a hemiacetal or an acetal. So then you have to recognize that oxygen will need to be attached to that carbon, so there's your ring. So 1, well, it's 1, whoops, get rid of that. Okay, so this needs to be attached there. So 1, 2, 3, 4, so this will be a 5-membered ring. And oxygen will be part of that ring. Okay, so we said oxygen was 5, so 4, 3, 2, and 1. So what's going to happen to the OH? Oxygen is going to become an OH, right? And 1 also has a CH3 on it. 2 and 3 are CH2s, and 4 has an ethyl group on it. So that would be your hemiacetal. So in this case, we're not going to add another alcohol. So once you've made that cyclic hemiacetal, so that's different than this cyclic hemiacetal. Well, that was the last lecture, right? With the ethylene glycol, because that had 2 OHs in the same molecule. This one only has 1, so it's typically going to stop there at the hemiacetal. Like it's only got 1 OH in the molecule. Okay, so this is a very important reaction in biological chemistry, because here we have an aldehyde, and here we have lots of alcohols. So this alcohol could react there, but that would make a 3-membered ring, right? This one could react there, but that would make a 4-membered ring. And 3 and 4-membered rings are not favorable. That alcohol could react there, that would make a 5-membered ring, which is okay. Or this alcohol could react there, and that would make a 6-membered ring. And making 5 and 6-membered rings are more favorable. 6-membered ring is particularly favorable. So this is going to make a cyclic hemiacetal. Oops. Okay, so if this is carbon 1, 2, 3, 4, 5, and that oxygen is 6, so this is 6, 1, 2, 3, 4, and 5. Okay, so the C11O becomes an OH, and then, so we won't worry about the stereochemistry here. So when we get to the carbohydrate chapter, because this is a carbohydrate, then we'll worry about the stereochemistry. So for now, 2 has an OH, 3 has an OH, 4 has an OH, 5 has the oxygen 6, which became part of the ring, and it's got this CH2OH on it as well. And so what's the functional group here? Well, there's several, but this carbon here is the hemiacetal. right? Because that carbon has an OH, and it's got the OR group attached to it. And then the other carbons are just alcohols. Right, because they only have one OH attached to them. But anyway, carbohydrates are obviously very important in biological chemistry, and these making carbohydrates tend to exist in these cyclic hemiacetal forms. Okay, one more reaction in this lecture, and then we'll look at a synthesis problem. So this reaction is what's known as the Wittig reaction, which was worthy of a Nobel Prize in 1979. So you take an aldehyde or a ketone and react it with this thing. So you have a phosphorus double bonded to carbon, and then whatever's attached to carbon, hydrogen, or some alkyl group. So predicting the product is easy. Basically, phosphorus ends up double bonded to oxygen, and then this carbon ends up double bonded to that carbon. So you make an alkene. So you make a carbon-carbon bond, so that's a significant reaction, and you make an alkene, and of course you know alkenes can undergo lots of reactions, so they're very synthetically useful, which would be one of the reasons why this won a Nobel Prize. It's a very synthetically useful reaction. So oxygen comes off double bonded to phosphorus, so you make this side product called triphenylphosphine oxide. Okay, so this thing is what's called a yelid, and this is the yelene is a resonance form of it. So if we take the lone pair of electrons, make a double bond to phosphorus, then we have the yelene version. So let's go through how do you make the yelid. So what is a yelid? It's a neutral molecule, so overall this has a negative and a positive. So it's got no charge, it's neutral. And it's got oppositely charged atoms, and each of those atoms have an octet bonded to each other. So that's what a yelid is. Right, that carbon has an octet, it's negative. That phosphorus has an octet, it's positive. Opposite charges on adjacent carbons where both atoms have an octet, that's called a yelid. And if we look at its resonance form, that's called a yelene. Okay, so how do you make it? You start with triphenylphosphine, which is a very good nucleophile. So phosphorus attacks carbon, so you'd react it with an alkyl halide typically, or something with a good leaving group, so that the phosphorus can attack the carbon and kick off the leaving group, and that's just an SN2 reaction. And now you take this and react it with a strong base. So what's significant here is that the carbon next to phosphorus, which is positively charged, are fairly acidic. Well, they're not fairly acidic, but they're acidic enough that if you react it with a strong base like butyl lithium, you can take one of those hydrogens off. So let's take the 2 electrons in the carbon-lithium bond and make a bond to hydrogen. And these electrons become a lone pair on carbon. So then that would give you butane as a side product. And then what was the counter ion to phosphorus being positive was bromide, right? Because you lost a bromide. So then you would make lithium bromide and butane as side products. But we're mainly interested in the organic product. So now carbon has a lone pair and a negative charge, so that's your yelid. Okay, so how does this react with aldehydes and ketones? So let's take the yelene and react it with aldehyde or a ketone. So if we line it up like this, so phosphorus is next to oxygen, and then carbon of the yelene is next to carbon of the aldehyde or ketone. So these 2 electrons go here, and these 2 electrons go there. And you make what's called an oxaphosphatane, which is not stable, and this decomposes. So take those 2 electrons, make a phosphorus oxygen double bond, and those 2 electrons and make a carbon-carbon double bond. And now you have the alkene and your triphenylphosphine oxide. So phosphorus forms very strong bonds to oxygen, which is one of the driving forces for that reaction. But what we're interested in is the alkene. Triphenylphosphine oxide is just an impurity that's kind of hard to get rid of, but so you have to do some purification at this stage. But you've made an alkene, right? And so predicting the products of yelid reactions again are easy. Just take whatever's double bonded to phosphorus and double bond it to carbon instead. So whatever is double bonded to phosphorus, so we're going to take this and we're going to double bond it here instead, and oxygen is going to go to the phosphorus. So you would make that, and you would make triphenylphosphine oxide side product. Okay, so let's use some of the chemistry we've learned so far in this chapter to do this synthesis problem. So we want to make an alkene. Well, we just saw a reaction that makes alkenes. We could have made this alkene by, if we had that ylid and we had that ketone. And so how do we make ylids? So we just saw that we make ylids from alkyl halides. Oops. Reacting with triphenylphosphine, and then a base butyl lithium. Right, so we don't have to show this in the synthesis, but just so that you see another example. So you would make that, and then you would throw in a base, which would deprotonate. That carbon, right? It would take off this hydrogen to make the ylid, and I just draw it in the yielding form instead because this is how it's typically drawn. Okay, so we've shown how to make that, so now let's show how to make the ketone. So how could you make the ketone? So once we have these two, then we react them together to make that. So how do we make the ketone? Well, you could have made the ketone, well, we didn't finish this, did we? So we could take cyclohexane and make bromocyclohexane with Br2 and white, do a free radical bromination. Once we have bromocyclohexane, react it with triphenylphosphine, and then take that and react it with butyl lithium, and then we have the Wittig reagent. Okay, now how do we make the other partner? How do we make the cyclohexanone or cyclopentanone? Well, if we had this alcohol, if we had cyclopentanol, we could oxidize it, right? If we had cyclopentanol, we could oxidize it to make cyclopentanone. And so how could we have made cyclohexanol or cyclopentanol? We could have made it from bromocyclopentane. So just like an SN1 or an SN2 reaction. So basically we would take cyclopentane, make a bunch of bromocyclopentane, and then take half of that and make the Wittig reagent, and take the other half and make cyclopentanone. And then once we had those two made, then we would react them with each other to make the final product. Okay.